Taking over from Luigi Accardi now, we'll have Sivaguru Sritharan, followed by Peter Hislop as the second talk of this session, and then Luigi Accardi will be the first person to speak after lunch, the only mathematical talk before the party begins. So without further ado, and to try and keep us on time, I'd like to welcome Sivaguru Sritharan to tell us about stochastic Navier-Stokes equations and its connection to infinite dimensional analysis.
Thank you very much. First of all, happy 75th birthday for Professor Kalyan Sinha. And actually, you know, I belong to not really the quantum probability community, even though sometime in late 90s I bought Professor Parthasarathiy's book and have diligently read over the years and show and notice some machinery which can be probably benefit the Navier-Stokes community. By the way, you notice that I remove my tie and blazer because I have a dual life, but it's difficult to talk and think with those things on. So what I will do is, I thought sort of an introduction or invitation, so to speak, on Navier-Stokes equation and stochastic Navier-Stokes equation. There are many issues, right? If you stay in deterministic, some of the big questions are, one of the, of course, big question is the global unique solvability in 3D. When you start asking control theory equations, there are other challenging questions. But when you go to stochasticity, stochastic Navier-Stokes, a whole series of very interesting questions come. And in the last several years, you may have noticed many papers. And so if you are an outsider, this functional analysis wilderness of Navier-Stokes literature, I thought maybe I'll cut through and show you some of the results and some of the structure. I picked one theme, essentially Navier-Stokes equation and its connection to PDEs in infinite dimension. And that might have some appeal to this mathematical community. So what we will do is we will start with what I call the abstract Navier-Stokes equation. So that will look like du by dt plus mu of au plus bu is equal to 0. So these are functions of, so you essentially have a single Hilbert space, but you can't work with single Hilbert space in Navier-Stokes. I will clarify that. But for the moment, let's say you know, you need, this is for t positive and u naught belongs to h. So what this hides is the classical formulation of the Navier-Stokes equation in coordinate system. So that looks like this, right? So it is du by dt plus u dot gradient u is equal to minus gradient p plus nu Laplace u, and then div u is equal to 0. You may ask what domain? That's actually not a big deal. 2D, it could be R2 and R3 because O may be bounded domain, exterior domain is exterior to a certain geometry, or domains which has outlets to infinity, which we in the field call it domains with non-compact boundaries, and they have their own peculiarities with regard to various properties of the function spaces, the spectrum and of the linearized operator and so forth. So let's say this is for u of xt. So x belongs to some domain, let's call it G. Rn. N is 2 or 3 is the most interesting one. People have looked at dimensions higher than 3, dimension 4, for example. So u of xt is called the velocity. And then p of xt is called the pressure. Okay, so with this, I don't want to crowd the. So this is defined in. Think of it like a, a container where you have liquid filled and you slush around, and the boundary. So the boundary velocity is 0, and then u of x0 is equal to u naught. X is an initial field, but that's a classical form. So what we do is to go to the abstract form. What you do is you come up with some function spaces. This goes back to the first well-known rigorous work, sort of with completeness, is due to Jean Leray in his thesis. So it is 1930s, and then Eberhard Hoff, 1950s, and O.A. Ladizanskaya, 1950s, a bit later, and then J. Lyons and his prodigy also contributed. So that function space looks like this one. H is u belongs to L2 G, div of u is equal to 0. So what you do is you start with the square integrable function. So obviously this has to be interpreted in the sense of distributions, right? And then u dot ndg is 0. So that looks peculiar because if you have an L2 function, you cannot define boundary, but this additional condition allows you to define that, also in the sense of distributions. And then you come up with another function space v, which is u belongs to h10 g and div of u is equal to 0. Those two are essentially good enough to go to that framework. So this looks like a PDE, but that looks very much like an operator, functional equation. So it's a lot easier to work with. So I had to define the operators A and B, and this nu is just a number. So I used to work for the Navy. Well, not military, but somehow I got this nice appointment to do full-time research in San Diego, Point Loma for many years. So at that time I used to say for a submarine, nu is equal to 10 to the power minus 10 or something like that. It's very, very small, right? So anyway, so I need to go from here to get to there. It was Lyons and Prodi are the ones most prominently advocated that framework, but which has now become standard. The father Lyons. So A is actually it is minus pH of Laplace u, where pH is essentially the operator projecting to h. So it's sometimes called Helmholtz projection. And B is so B of u, so A of u I should write. B of u is again projection of u dot gradient u, and if I apply projection operator to the gradient p, that is 0, because divergence free vector fields are orthogonal to gradients. So what happens is when you take this equation and apply this projection, this term goes away. So essentially you have this equation, and immediately for large class of domains G, A is densely defined, but I don't need to say that this is self-adjoint operator. That generates holomorphic semigroup. Okay, so So this means that I can define this holomorphic semigroup exponential minus a of at, and so this is just essentially in the complex plane. You can actually show that it's holomorphic in a sector like this. That's because the resolvent associated with this operator is analytic in a sector in a region like that, so that gives you a holomorphic semigroup. So that immediately gives you a good structure to deal with this problem, right? So this part looks like a heat equation, right? Everything is nice. So why is $1 million? So that is because that's because of this operator, which behaves, the nonlinear term which behaves differently for 2 and 3 dimension. And so to cut the long story short, it turns out that by just one, you hit this by U, take an L2 inner product, and you can immediately show this inequality. Ut h squared plus 2 nu 0 to t a half u of r h squared d of r is equal to u naught h squared. Okay. So we'll just one integration by parts. It's because of this. There's a very interesting property that bu u h is 0. It's an amazing property of the Navier-Stokes term. So that when you take an L2 inner product, the results you get is exactly the results of the heat equation. So this one immediately gives you a topology, right? If I throw this away, notice that this is uniformly bounded. So you have the topology L infinity 0t h, and then this one, if I throw that away, it gives the topology L2 0t v. It turns out that v is domain of a half. The Hilbert scale here comes immediately because A generates a holomorphic semigroup, so you can define its fractional powers and negative and positive. So that defines the function space. So this is these days is called Ledizensky space. I think it's probably should be attributed to J.L. Lyons and Eberhard Hoff. So the story goes like this. In 1951, Hoff proves that this. So once you have this equality, any approximation to that, this one finite dimensional projection also satisfies this inequality. So Eberhard Hoff proved that for 2 and 3 dimension, in a rather arbitrary geometry. So Eberhard Hoff and his that 2 and 3D, there exists a solution, a generalized solution, to the Navier-Stokes equation with finite Ledizensky topology. Let's call it LD topology, because it's easier to say that way. So what is the result? So the 2 and 3 dimension, there exists a solution. Just that in 2 dimension, staying with this topology, you can prove uniqueness. In 3 dimension, staying with that topology, you cannot prove uniqueness. That's sort of it's very easy to see, easy to work it out and see. So in 3D, so 2D, exactly following this topology in 1959, Lyons and Prodi, I should say it is J.L. Lyons, Father Lyons and Gaviono Prodi, proved that in 2D, the above class is unique. 3D is open. So that is the Millennium Prize problem, right? It's very cleanly stated. The Millennium Prize problem is that the initial data is L2, no boundary, I don't need any other forcing. We can show that 2D, 3D, 2 and 3D we have existence. There are different ways of proving existence. R3 also you can prove. Yeah, irrespective of the domain. There are some restrictions, pipes and so forth. We can talk about the flow through pipes and so forth. But in general, for rather arbitrary domains, this is true. 2 and 3D. So the domain is not an issue. It comes in a different way. We can talk about. So that's why I didn't make a big deal out of omega. What the domain looks like. The difference is because the difference is because when you try to prove uniqueness, you will write the first equation for, let's say, for U1, the same equation for U2, and then you write the difference. And so since it's nonlinear, the difference doesn't satisfy the same equation. There's a term that comes in. So you try to estimate that term using Holder inequalities and Gagliardo, Nirenberg, and so forth. Rather, that's what it was done 70, 80 years ago. We still don't know to do better. That's because of this following. It's called the Gagliardo Nirenberg inequality. Actually, to be fair, it was before they generalized it. People attribute to Ledzinski and Liray and all those people. For the case I am writing, is the following. If you have a L4 norm, right, this is again arbitrary domain. So that's what, so this is less than equal to two cases. U of L2 half gradient of U of L2 half for n is equal to 2 and U of L2 1/4 and gradient of U of L2 3/4 for n is equal to 3. So that's what is turned out to be crucial for the fact that you simply cannot overcome the geometry. Okay, so there's no other difficulty with respect to whether you can put smoother initial data. If you prove, start with the higher order Sobolev space initial data, you can prove local solvability. You can start with fancy Bezos spaces and whatnot. It's all local or Moray spaces and I have also worked along that line. So that's the Millennium Prize problem. Essentially, you will find that when you try to take the difference, you will end up with a situation like this. If you write U is equal to two solutions, U1 minus U2, then you can show that Z of L2 at time squared is equal to Z of Z naught of L2 squared exponential 0 to t gradient of U1 squared dr, this is R, for 2D. And this is replaced by exponential 0 to t gradient of U of L2 fourth dr for n is equal to 3. Okay, so I came to talk about infinite dimension. I am not there yet, but I just I thought this is so. So you can immediately see how in 2D the story closes, because you know that any solution when we prove uniqueness has this norm finite, right? That's the Hoff class solution. So you run to this and say, this is finite, and therefore if this is 0, then this has to be 0. 2D is thus solved. That's the famous proof of Lyon's problem. In 3 dimension, you do the same step and you end up with 4 here. But within this class, you go and look and find that you don't have the integrability of the fourth. This is what's called the N's trophy. Okay, so You'll say, oh, because these people didn't know how to start with smoother data, so you start with H1 data, you only prove local sort of routine time. Okay, so that's the Millennium Prize problem. And okay, now the issue I wanted to talk is to go back and what happens when you add a noise. Okay, so and so obviously, you know, all these are very fundamental problems, so they all have long history. And so if I want to randomize the situation. It was historically done in many different contexts, you know, statistical theory, turbulence, and so forth. So the first effort is again equal to by Eberhard-Hoff. So Eberhard-Hoff, 1952, because at that time, so he considered this problem that looks like deterministic, right? Belongs to H. But he said, okay, suppose instead mu naught is given by a probability measure, right? So the law of U naught is given by a probability measure that defines on Borel algebras of this Hilbert space. So, and then how does this measure propagates? So that's the in fluid mechanics, that is the theory of statistical solutions. You know, goes back to G.I. Taylor and Kolmogorov looked at the stationary solutions and so forth. So that's I will come back to Hoff's formulation in a moment once I go to the stochastic problem, right? So it's important to leave. So remember this, that the 2D, this story becomes what's called a part-wise solution in the stochastic once we go to stochastic, because only we have randomized the problem. And the energy estimate I showed can be used to prove existence of martingale solutions, which means the probability laws defined on regarding this as the path space. Okay, so that's so there were many other people looked at, but when I went into the field, I had this single-minded: is that what is the corresponding stochastic counterpart of Hoff, Lyons, and Prodi? Right, the picture I showed. That's the condition I was most interested in. A lot of very smart mathematicians contributed to this subject, so I want to be careful when I say who and who did what. So you may ask, okay, what if there's so that's Hoff's statement of starting with initial data that is probabilistic. How about if you add noise? What kind of noise you can add? Gaussian noise you can add. So that, you know, to be honest, it started with Eugene Novikov. He's more of a theoretical fluid mechanics in 1963. But he only derived the Kolmogorov equation. The rigorous work was started with Bensusan and Timam. So Alan Bensusan, I think I even, this is what happens when you go into administration. Now you forgot how to spell Bensusan. And Timam in 1973. This paper actually was in French, so I had to take a great deal of effort to read it. So they looked at roughly the case we are going to describe, but not quite the case I described. So you know that when we want to have put this in the stochastic form, you want to write it in the Ito form. So here is the, so essentially you multiply through because the right hand side should look like stochastic integral. So you write nu of A of u plus B of u dt is equal to, let's put dw now, right? So I want to first explain the functional framework associated with this this problem. So you can still regard q naught in H. So let's stay close, very close to the Leray-Hoff Lyon's Prodi picture, so that you don't see everybody coming up with their own. So the first thing you use, you are going to have is what's the counterpart of this one, right? What's the counterpart of this? And what is W, right? And when I used to spend time with Professor Kalyan sitting down and discussing in Chapel Hill. So he doesn't like this. He would want me to write this as a Brownian sheet and show the time difference, time derivatives and so forth. Okay, so essentially the first thing I wanted to show is that we have an exact counterpart of this and that, provided W has some properties. And then I will start asking questions of can we talk about optimal stopping that leads to a variational inequality in infinite dimension? Can you talk about impulse control? It leads to a quasi-variational inequality in infinite dimension. And then control type questions and so forth, nonlinear filtering. Okay, so the first result, I need to characterize W. So let's take W. In the simplest case, more general ones, there's actually Levy. I spent time on writing about those all as well. So let W T be an H valued Wiener process. So need to say something about that. So we will say let W be an H valued Wiener process with trace class covariance operator Q. So this means that expectation of Wt acting on some function phi taken inner product, W tau acting on some function psi taken inner product. So now you get two scalar Brownian motions, and this will be equal to T smallest of that, and the operator Q acting on phi psi H, and with trace of Q finite. Okay, so let's work with that. Then it can be shown by applying Ito formula. So apply Ito. It's not applied formally. You have to rigorously justify. There are unbounded operators come in. For a function, let's say fu is equal to u of h squared. Because I want to generate the counterpart of just multiplying by, taking an inner product with u is applying Ito formula to that. So apply Ito formula and then take expectation. So when you apply Ito formula, I get a martingale term. Particularly this one, I get a global martingale term. If I have a multiplicative noise, then I get a local martingale term. Need to work. I had to say some more. So, but you apply the Ito formula and take expectation. Then you wipe out the martingale term, and then you end up with x of ut h squared plus mu 0t gradient u r. So did I write a half? Let's write a half. They are saying u of r dr is equal to expectation of u naught h squared plus the final time t times trace of q. It's a very beautiful formula. It comes up. This essential exact counterpart, which is what the theory, the aspect of the theory or the approach I like, because then you get the exact counterpart of the original Lyon's, Hoff work. What is the difference? There's an expectation here, and there's one more difference. We have this term T times trace Q, the energy contribution from the noise, and that also explains why I have this condition. Okay, so if I put Q is equal to I, it's an open problem. So you see many papers in stochastic Navier-Stokes, but the moment you put Q is equal to I, things get wiped out. You don't have it. It's because it's under this condition there is your Q has eigenvalues, so they are lambda E and phi. Then the WT can be expanded. Square root of lambda I phi times one-dimensional Brownian motions, right? So you have that nice representation, and the fact that the sum of eigenvalues is finite, it helps you to. So you have so if the trace Q is finite, then you get two results. The counterpart of Hoff's results, that there exists a martingale solution to this problem. So I'll tell you how that the functional framework I set up for that. So first you can prove that there exists a pathwise solution in Ledzinskaya topology that is unique. In 2D. So that result is actually due to J.L. Mainaldi and myself. So to prove exactly in the topology, we use what's called the local monotonicity property of this operator. This operator is not maximally monotone like in Minty-Browder theory, because then everything is done. You have global solvability. But it's only locally monotone and in some L4 balls and so forth, so you can complete that. And then the counterpart of Hoff's results, in order to do that, I need to come up with the path space, which I will take very much similar to the path space I took over there, omega of a half, Ledzinskaya. So the Ledzinskaya space, which was on the PDE side, become my omega, on which I define the probability measures. So then I will have a probability measure P that defines on Borel sets of omega into 0, 1, such that the equation is satisfied, so star is satisfied in the sense of Strook and Verdun. So Strook and Verdun's the paradigm is that instead of looking for pathwise solution, you look for the probability measure defined on the path space with sigma algebra is defined on that, and the canonical filtration. You show that for that probability measure, this part, if you keep this part, is a martingale. So that will, you can, yes.
You have continuous trajectories.
Yeah.
Paths
Yeah.
are continuous.
Yeah, almost sure. Yeah, but here, I don't work with that topology. There's a reason why we don't work with space and continuous functions, because balls in the space and continuous functions are not weak star compact, right? So it's not useful. Actually, I also had intersection with Skorohov space, domain of A minus half. So essentially, you have weak topology here, weak star here, because a ball in that is weak star compact, and that's the reason why we don't work with continuous function. And weak topology here. So the intersection actually, if you want to apply approximations and take limits, you need Prof theorem. But the Prof theorem is not useful here because this is not Polish. So this is actually called Lucene space. So that's when I first started reading Professor Parthasarathhi's book, where the extension, Varadarajan's famous extension of Prof theorem to Lucene spaces is described in Professor Parthasarathhi's book. Good place to read. And anyway, so you can actually show that there exists a probability measure defined on the space-time topology, such that this solves the martingale problem. In fluid mechanics, that is called space-time statistical solutions. Okay, but in stochastic analysis, it's called the martingale solutions. So you can prove that the martingale solution exists for 3D, just like, but is the martingale solution unique? The only method I knew how to solve, and this is what other people use, going back to Bensusan and Kimam, Flandoli and others, is to resort to what's called the Yamada-Watanabe technique. So this means that if you know is pathwise unique, and if you have the martingale solution, then the martingale solution is unique. But so that means that you can, you go back to pathwise, you go back to deterministic problem in essence. Unless it's a multiplicative noise, then you do a little bit more work, because when you subtract, the noise goes away in a simpler setting. So it's pathwise unique in 2D. The 3D looks very much similar to Hoff construction, just that you work with probability measures instead of sequences going to limit. This time you have probability measures converging. So good. That's the introduction I wanted to give. How many minutes I have?
1.
Huh? 1 minute? I'll take 2.
You'll have less questions.
Pardon?
You'll have less questions.
Yeah, no questions. So let's go to. I wanted to talk about. So once you have, well, it's okay. I think the justice is done in the sense of explaining the Navier-Stokes theory. So you go to stochastic Navier-Stokes, then of course solvability. That's a question you can ask, and which I just answered. The other one is invariant measures. And ergodicity. The third one is large deviation. So this Sundaran, Padmanabhan Sundaran, I did this work for zero noise problem. After that, Donskoy-Varadhan type results was also done by others. The other question you can ask is a stopping time problem and impulse control. And finally, nonlinear filtering. Okay, so let's, I want to go to the infinite dimensional problem and say a few words, because the ergodicity itself will take some time to talk. So let's look at this operator. Let me call it n, n of phi. That looks like this. Trace of q, dxx phi, minus ax plus b of x dx of phi. So, if you go back and if I don't have the stochastic Navier-Stokes equation, if I don't have that term, the Kolmogorov operator looks like this, right? So when I have this drift, then the Kolmogorov operator will be the drift multiplied by the first derivative, right? So this is essentially the backward Kolmogorov, or the generator of the semigroup, the formal generator of the semigroup. So the issues I have in mind are, for example, if I jump and ask the stopping time problem, then I get actually a variational inequality. So the first question you ask is, of course, d phi by dt is equal to n of phi, the solvability problem, right? And then the second question I ask is, if it is an optimal stopping, then I have also some g, and this is some g, so I have a variational inequality connected to that, and so that can be translated into a problem like this: d phi by dt, so minus n of phi plus n of k of phi belongs to 0. So 0 belongs to it. This is essentially the normal cone associated with this second constraint. So, for example, one of the developments Viral Babu and I did, V. Babu, is the following. You show that this operator is so this combined operator, which we call script A of phi. So script A of phi is M accreting in L2 mu of h, and that's how we solve this problem. So that's like maximal monotone operators in PDE theory. So what is this mu? This mu is the invariant measure associated with this stochastic evolution. So since it's 1 minute, I'll say 1 minute story about invariant measure and I'll finish. Okay? And so the type of questions I have will usually center around that operator. So this is what I came to speak about. Got carried away about millennium price. So that's about this infinite dimensional PDE, because here the little x is, belongs to the Hilbert space. So let's I say a few words about the invariant measure and ergodicity, and then we'll quit. So let's define an operator PT acting on phi as expectation of phi acting on the solution of the Navier-Stokes, stochastic Navier-Stokes. Okay. Then we can show that PT maps continuous bounded functions into continuous bounded functions. So it is Feller semigroup. So the stochastic Navier-Stokes, it generates a Feller semigroup in the 2D case, right? So you need actually, so there's a famous paper by Flandoli and Maslowski. He showed that if you have, if P T is strong Feller and irreducible, then the invariant measure is unique. So by the way, the existence of invariant measure essentially follows the corresponding energy estimate I showed. So with that, the You can use some compactness theorem and show that there is a measure. Just that there are many. In fact, you know that steady Navier-Stokes has many solutions. You can just plug in well known. And therefore, if you have a direct measure sitting on a steady solution in Navier-Stokes, you have many solutions. So you know that the invariant measure is not unique Navier-Stokes. And the strong Feller property is actually PT maps bounded functions into continuous functions. So that is the irreducibility, of course, is easier to prove. That's connected to controllability of the corresponding deterministic problem. The strong Feller doesn't come easily. So they put a lot of conditions on the with respect to this Q. Right? I won't write it down here. Something to do with is degenerate, but at the same time non-degenerate. That was relaxed by Martin Herer actually in his work, seminal work. He showed that you only need to have 4 modes in that expansion I showed. You only need to have 4 modes. So he replaced the Feller with what's called asymptotic strong Feller. So this is a strong Feller. You know, regular Feller goes from bounded to continuous function. Strong Feller goes from Borel function, bounded Borel function to continuous. So it has a smoothing property. Anyway, so we need to extend that semigroup to these function spaces, right? So with the once you know that the invariant measures are unique, and then you can use that to essentially bring the well-known PDE theory, monotone operators, nonlinear semigroups, and so forth in this space for the infinite dimensional problem, and thereby answering some of the questions related to controls and optimal stopping and so forth. This is the idea I wanted to. So the issue is open the moment you don't have an invariant measure. And so you may ask, why did you use the invariant measure? Why don't you use Gauss measure? There you can integrate by parts and so forth. But for Gauss measure, you know, there's one thing I didn't tell you. If you know studied, you know, from Pasi semigroup, the first thing you start is you need the closure of the operator. We don't know whether the operator is closed if you use Gauss measure here. I know Rottner wrote many papers, but I don't think he proved the operator is closed. So if you don't have a generator that is closed, the semigroup Hilly-Yoshida type things you can't extend. Never mind the more powerful Crandall-Liggett or Komura-Kato we used here. When you have a maximal monotone, you know, normal cone is maximal monotone. So the sum is maximal monotone by some theorems, Rockefeller and so forth. Anyway, so that I just wanted to give an idea of the type of machinery comes in when you ask questions of this type, questions of filtering, questions of control, optimal stopping, and so forth for stochastic Navier-Stokes. Thank you very much.
So we have something in the order of -4 minutes for questions.